Hi there, my name is Ellie Maurer, and today we are going to be talking about local, resting, and action potentials. To start out, this is a neuron, and some of the parts of the neuron that we're going to be talking about today are the dendrites, the soma, the axon hillock, which is right here, and the axon. In a neuron, its normal state is called a polarized state, also called a resting membrane state. In a resting membrane state, the ICF, or the inside of the neuron, is negative and it is filled with potassium ions, while the outside of the neuron, or the ECF, is positive and it is filled with sodium ions. If a stimulus, let's say, starts at this dendrite right here, it creates a local potential, and a local potential is a short-range change in voltage along the plasma membrane, this thing right here. And in a local potential, it starts to open sodium gates, which causes neighboring sodium gates to open. Some of the characteristics of a local potential is that it's graded, which means the magnitude varies, meaning the stronger the stimulus, the more gates open. It is also decremental, meaning the current weakens the further from the source you get, or the further from the stimulus. It is also reversible, which means that the resting state continues when the stimulus stops. Now, if this local potential gets strong enough and reaches the axon hillock, it will trigger an action potential. But this is only if it reaches the threshold of negative 55 millivolts. And an action potential is a local potential is when it moves the stimulus down the axon. Some of the characteristics of an action potential is that it follows the all or nothing law, which means it only happens if the local potential reaches the axon hillock right here, and that makes it not graded. It is also non-decremental, which means it maintains its full strength as it moves down the axon. And it's irreversible, which means it cannot be stopped as it moves down the axon. So, all of this put into steps. We start at 1, which is negative 70 millivolts. And this is at its resting membrane state. And when a stimulus occurs in that dendrite right there, it goes up, and it's strong enough, it goes up to the threshold of negative 55 millivolts, and then it triggers the action potential, which causes depolarization. Now, depolarization is when the sodium gates open, allowing sodium ions to flood into the ICF, making it become positive, and that causes its millivoltage to rise up to its peak action potential, which is 35 millivolts. And when that happens, the potassium gates start to open, and that causes potassium to flood outside of the ICF, causing its voltage to go down all the way below the resting membrane state voltage. And this process is called repolarization. And at that point, when it's below its resting membrane state, it goes back up. When at that point, the potassium gates close, and that means it's going into recovery, and then it goes back to negative 70 millivolts. A really good image. These in the video lectures, these images really helped me to understand exactly what was going on. You can see it starts out. This is where it starts. This is the action potential, and you can see that it changes the ICF to become positive and the ECF to become negative. And this is right here is when it goes into recovery, and then it goes back to its resting membrane state. And then you can see it going down the axon more, making it positive, and then going back to negative, and then it continues along the axon. And that's what I have to say about local and resting and action potentials. Thank you for listening.